In 2003, two cosmologists, Lawrence Krauss and Robert Scherer, did a calculation. It was not a particularly complex one. It was based on something that scientists had only recently confirmed, something that had earned its discoverers a Nobel Prize a few years later. The universe was not just expanding, its expansion was speeding up. Dark energy was pushing everything apart, faster and faster. Krauss and Scherer took this new fact and ran with it. They asked a simple question. What does this mean for the very, very distant future? The answer they found was profound and deeply lonely. They calculated that in about 100 billion years, every single galaxy outside of our own local group, the cluster of galaxies gravitationally bound to our Milky Way, would be gone. Not destroyed, just gone from view. The accelerating expansion of space would carry them away from us so fast that their light would no longer be able to reach us. They would cross a cosmic event horizon, an unbreachable point of no return. Future astronomers living in that distant epoch would look out into the night sky with their telescopes. They would see their own aging galaxy and its nearby companions, and beyond that, they would see nothing. Just an endless, featureless black void. They would have no evidence that other galaxies ever existed. They would have no evidence of the Big Bang because the cosmic microwave background radiation, the echo of that initial event, would have stretched to wavelengths so long they would be undetectable. Their science would lead them to a logical but completely wrong conclusion. They would conclude they lived in a small, static island universe alone and without a beginning. Our entire cosmic history, all the knowledge we have painstakingly gathered, would be erased by the simple, relentless expansion of spacetime. The fate of the cosmos is to forget itself. This story is not just about the end. It is about how the very smallest things we know, the strange rules of the quantum world, are, the architects of that beginning, that middle, and that, final, lonely end. Number 16, the universe is a two-dimensional hologram. A spoonful of a neutron star weighs about 4 billion tons. A region of space the size of a proton, if it contained enough energy to become a black hole, would have a mass energy equivalent of a large mountain. Yet, the information needed to describe everything inside that black hole, according to some of our best theories, could be written on its two-dimensional surface. Not within its three-dimensional volume, on the surface. This is the core of the holographic principle. It was born from the mind-bending physics of black holes in the 1970s and 80s. Jacob Bekenstein and Stephen Hawking were studying black hole thermodynamics. They found something bizarre. The entropy of a black hole, which is a measure of its information content, was not proportional to its volume, as you would expect for any normal object. It was proportional to the area of its event horizon, its surface. It was as if all the 3D stuff that fell into the black hole got smeared out and encoded on its 2D boundary. This was a clue. A deep one. Physicists Gerard Hooft and Leonard Susskind picked up on this clue in the 1990s. They proposed that maybe this was not just a weird feature of black holes, maybe it was a fundamental principle of the entire universe. Maybe our reality, the three-dimensional world we experience with all its depth and volume, is just a projection. A hologram, the real fundamental physics might be happening on a distant, lower-dimensional boundary surface, and what we perceive as reality is just the projection of that information. It sounds like science fiction, but in 1997, a physicist named Juan Maldacena gave it a concrete mathematical backbone. He produced a stunning theoretical result called the 8S CFT correspondence. It showed a precise mathematical equivalence between a theory of gravity in a certain kind of five-dimensional spacetime, the 8S part, and a quantum field theory without gravity on its four-dimensional boundary, the CFT part. They were two different mathematical languages describing the exact same physics. You could solve a hard problem in gravity by translating it into an easier problem in the quantum field theory on the boundary, and the answer would be correct. This was a revelation. It provided a working model, a toy universe where the holographic principle was demonstrably true. It suggested that the universe we see, with its 3 spatial dimensions plus time, might be a holographic projection of information stored on a 2-dimensional surface at the cosmic horizon. The stuff of the cosmos, the galaxies, stars, and us, might be like the image on a television screen generated by information encoded in a flat surface. What does this mean for the fate of the cosmos? It completely changes the questions we ask. If, the universe is a hologram, then, the ultimate reality is information. The Big Bang might have been the moment this information was first encoded. The expansion of the universe could be the projection of this information unfolding. The ultimate fate, whether a big freeze or a big rip, might be described not as the death of matter and energy, but as the final state of this cosmic hard drive. Questions about what happens to information in black holes, or whether information can be truly destroyed, become central to the fate of everything. The universe might not end in fire or ice, but with the last bit of information reaching its final static state on a distant cosmic boundary. The entire 3D drama of the cosmos could be just a shadow play, and the real story is written in a language of quantum bits on the edge of space-time itself. Number 15, spacetime is woven from quantum entanglement. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper describing a phenomenon they believed proved quantum mechanics was incomplete. It was called quantum entanglement. Einstein famously called it spooky action at a distance. It described how 2 particles could be linked in such a way that measuring a property of one particle, like its spin, would instantly influence the corresponding property of the other, no matter how far apart they were. Faster than the speed of light. This violated Einstein's cherished principle of locality, the idea that no influence can travel faster than light. In that same year, Einstein and Rosen wrote another paper. This one was about general relativity. They explored a mathematical solution to Einstein's equations that described a bridge connecting 2 distant points in spacetime. This bridge, a kind of tunnel through the fabric of reality, later became known as a wormhole or an Einstein-Rosen bridge. For decades, these 2 ideas, quantum entanglement and wormholes, lived in separate houses of physics. One was a cornerstone of the bizarre quantum world, the other a curious speculative feature of gravity and space-time geometry. Then, in 2013, Leonard Susskind and Juan Maldacena proposed a radical new idea that connected them. The idea is abbreviated as ER equals CPR, a shorthand for Einstein-Rosen bridges equal Einstein-Podolsky-Rosen. Their conjecture is simple and profound. A wormhole connecting 2 points in space is the geometric gravitational description of 2 particles being quantumly entangled. They are not just related, they are the same thing described in 2 different languages. This suggests something stunning about the nature of reality. It implies that space-time itself, the very fabric of the cosmos, is not fundamental. It is an emergent property. It is built from or woven out of the connections of quantum entanglement. Think of it like a fabric. Like, the individual threads are not the fabric. The fabric is the pattern of how the threads are woven together. In this view, quantum bits of information linked by entanglement are the threads. The geometry of space-time, the shape of the universe, is the pattern of their weaving. The more entangled 2 regions of space are, the closer they are in a geometric sense. A wormhole is just a highly entangled direct connection. This idea offers a new way to think about the universe. The Big Bang might not have been an explosion of matter and energy into a pre-existing space. It might have been a moment of massive universe-wide entanglement. The subsequent expansion of the universe could be seen as the evolution of this entanglement network. It also offers a potential resolution to the black hole information paradox. When something falls into a black hole, maybe the information is not lost. It becomes entangled with the Hawking radiation that slowly leaks out. The ER equals EPR idea suggests that a wormhole connects the interior of the black hole to this radiation, providing a path for the information to escape. The ultimate fate of the cosmos looks different through this lens. The Big Freeze, the heat death of the universe, would be a state where all entanglement has been maximized and evenly distributed. There would be no more complex structures, no more interesting connections, just a uniform sea of weakly entangled particles. The connections that build spacetime would become so simple and homogeneous that nothing of interest could ever happen again. The universe would not just grow cold and dark, its very geometric structure, built from these quantum links, would become featureless and static. The spooky action that once built galaxies would settle into an eternal, unchanging silence. Number 14, our universe could be just one bubble in an endless foam. The vacuum of space is not empty. According to quantum field theory, it is a roiling, chaotic foam of virtual particles popping in and out of existence on incredibly short timescales. For a fraction of a second, a particle and its antiparticle can borrow energy from the vacuum, exist, and then annihilate each other, paying the energy back. This happens everywhere, all the time. The seemingly placid void is actually a cauldron of quantum activity. In the 1950s, physicist John Wheeler took this idea and applied it to space-time itself. He suggested that at the smallest possible scales, the Planck scale, about 1.6 × 10 raised to the power of 35 meters, the geometry of spacetime is not smooth. It is a chaotic, bubbling quantum foam. Tiny wormholes and short-lived Bobby universes might be constantly popping in and out of existence, just like virtual particles. Most of these fluctuations are microscopic and vanish almost instantly. But what if one of them did not? What if a random quantum fluctuation was large enough and energetic enough that it did not collapse back into the foam? What if it began to expand? This is a theory of cosmic origins known as quantum fluctuation cosmology, first explored by physicists like Edward Tryon in the 1970s. Tryon famously remarked that the universe might be simply one of those things which happen from time to time. The idea is that our entire observable universe could have started as one such lucky fluctuation in a pre-existing space or a meta-universe. This has a profound implication. Our Big Bang might not have been a unique, singular event. It could be a common, everyday occurrence in a much larger, older reality, like our universe could be just one bubble in an endless effervescent sea of cosmic foam with new universes bubbling up all the time. Each universe would have its own Big Bang, its own expansion, and its own ultimate fate. This idea connects directly to the fate of our own cosmos. If our universe can be born from a quantum fluctuation, perhaps it can also die by one. Speculative, but terrifying idea is the concept of vacuum decay. You know, our current vacuum, the state of lowest energy in the universe, might not be the true absolute lowest energy state. It might be a false vacuum, a metastable state, like a ball resting in a small divot on the side of a large hill. It is stable for now, but it is not perfectly stable. Quantum mechanics allows for a phenomenon called tunneling. A particle can spontaneously pass through an energy barrier it should not be able to cross. A bubble of the true vacuum, with a lower energy state, could spontaneously appear anywhere in our universe at any time due to a quantum tunneling event. This bubble would be catastrophic. Inside it, the laws of physics as we know them could be different. The properties of elementary particles, the strengths of fundamental forces could all change. This bubble of true vacuum would expand outwards at the speed of light, converting our false vacuum into the true one. We would never see it coming. One moment, the universe is here. The next, it is replaced by something completely different and utterly hostile to our form of existence. The end of the universe would not be a slow fade to black, but a sudden, instantaneous rewrite of reality triggered by a single, random quantum event. Number 13, the laws of physics are fine-tuned for our existence. The strength of gravity is a specific number. If it were slightly stronger, the universe would have collapsed back on itself moments after the Big Bang. If it were slightly weaker, galaxies and stars would never have formed. The strength of the electromagnetic force that holds atoms together is another specific number. If it were a little different, stars would not be able to create carbon, the basis of life. The mass of the neutron is slightly heavier than the mass of a proton. If it were the other way around, all protons would have decayed into neutrons, and atoms would not exist. The list goes on and on. There are about 24 of these fundamental constants and quantities in physics. All of them seem to have values that fall within a very narrow life-permitting range. It looks, for all the world like the universe was set up or, fine-tuned, for the eventual emergence of conscious observers like us. This is the fine-tuning problem, and it sits at the uncomfortable intersection of physics and philosophy. One proposed solution to this puzzle is the anthropic principle. The principle comes in several forms, but the most discussed one is the weak anthropic principle. It states that the reason we observe the universe to have these specific life-permitting values is because if it had different values, we would not be here to observe it. It is a selection effect. It is like asking why we find ourselves on a planet with liquid water and a breathable atmosphere. It is because we could not have evolved on a planet without them. There might be countless dead planets out there, but we only find ourselves on a living one. This is where the quantum world meets the cosmos. Many theories that arise from quantum gravity and string theory naturally predict not one universe, but a vast, perhaps infinite, number of them. This collection of universes is called the multiverse. For example, the theory of eternal inflation suggests that our Big Bang was just one of many, creating an endless fractal-like structure of bubble universes. Each bubble could have different fundamental constants, different laws of physics. In this context, the anthropic principle becomes a powerful explanatory tool. If there are 10 raised to the power of 500 possible universes, as some versions of string theory suggest, each with a random set of physical laws, then it is no longer surprising that we find ourselves in one of the rare ones that can support life. We lost the cosmic lottery in the vast majority of universes, but in an infinite multiverse, it is inevitable that some universes, by pure chance, will have the right settings. We are simply living in one of those lucky bubbles. The fate of the cosmos is tied into this. The fine-tuning of dark energy is particularly puzzling. Its value is incredibly small, 120 orders of magnitude smaller than theoretical predictions. If it were much larger, the universe would have expanded so fast that no structures could have formed. If it were negative, the universe would have quickly collapsed. In a multiverse scenario, this is not a problem. There are universes with all possible values of dark energy. We just happen to be in one with a small positive value. This small value dictates the ultimate fate of our universe, a long, slow, accelerating expansion leading to a cold, dark, empty future. The very reason our cosmos will end in a big freeze, and not a big crunch or a big rip, might be because that is one of the few fates that allows enough time for life to evolve and ask the question in the first place. Our existence and our ultimate doom might be two sides of the same anthropic coin. Number 12, the end of the universe could be the beginning of the next. The second law of thermodynamics is one of the most fundamental laws in physics. It states that the total entropy, a measure of disorder or randomness in an isolated system, can only increase over time. The universe, as a whole, is an isolated system. This law dictates its ultimate fate. The universe started in a very low entropy state, a highly ordered, hot, dense point. It has been getting more and more disordered ever since. The ultimate fate predicted by this law is the heat death of the universe, or the big freeze. A future where all the stars have burned out, all the black holes have evaporated, and all that is left is a cold, uniform, maximum entropy soup of stray particles. A state of perfect equilibrium, from which nothing interesting can ever happen again. But what if that is not the end of the story? Sir Roger Penrose, a Nobel laureate and mathematical physicist, proposed a radical theory called conformal cyclic cosmology, CCC. It suggests that the end of our universe is also the beginning of the next one. The theory hinges on a clever use of quantum mechanics and relativity. Penrose's idea starts with the far future of our universe. After an incomprehensibly long time, trillions upon trillions of years, the universe will be composed almost entirely of massless particles like photons and gravitons. The massive particles like protons and electrons will be so far apart that their mass becomes negligible compared to the vast emptiness. According to Einstein's theories, massless particles do not experience the passage of time. From a photon's point of view, its entire journey from a distant star to your eye is instantaneous. They also do not have a sense of scale. A universe filled only with massless particles is conformally invariant, meaning its geometry looks the same at all scales. Here's the leap. Penrose argues that in this far future state, the universe, having expanded to an almost infinite size and being filled with massless particles, forgets how big it is. The concepts of big and small lose their meaning. At that point, the infinitely large, cold, empty universe of our future becomes mathematically equivalent to the infinitely small, hot, dense state of a Big Bang. The end of one aeon, as Penrose calls it, becomes the Big Bang of the next aeon. The transition is smooth. The vast, empty space of the previous universe is conformally rescaled to become the starting point of the new one. The very low entropy state of the new Big Bang is a consequence of the very high entropy state of the old universe, once all the information stored in massive particles and black holes has been radiated away. The arrow of time, driven by the increase of entropy, starts all over again in the new aeon. This theory makes a testable prediction. Penrose suggests that the Hawking radiation from supermassive black holes in the previous aeon could leave faint traces in the cosmic microwave background radiation CMB of our aeon. He and his collaborators have claimed to find faint circular patterns in the CMB data from the WMAP and Planck satellites, which they interpret as evidence of these Hawking points. This claim is highly controversial and not widely accepted by the physics community, but it represents a serious attempt to find evidence of a time before our Big Bang. If CCC is correct, the fate of our cosmos is not an ultimate end. It is part of an infinite cycle of rebirth, where the quantum evaporation of black holes in one universe seeds the cosmic fire of the next. Number 11, our universe might be a computer simulation. The screen you are reading this on is made of pixels. The image appears smooth and continuous, but if you look closely enough, it is composed of a finite number of discrete points. What if space-time itself is like this? What if, at the very smallest level, reality is not continuous but is pixelated, made of fundamental indivisible units of space and time? This is a core idea in several approaches to quantum gravity, like loop quantum gravity. The smallest possible unit of length is the Planck length, about 10 raised to the power of 35 meters. The smallest unit of time is the Planck time, 10 raised to the power of 43 seconds. This idea of a discrete, finite reality has led some physicists and philosophers to a startling conclusion: we might be living in a computer simulation. The argument, most famously articulated by philosopher Nick Bostrom in 2003, goes something like this. First, assume that it is possible for a civilization to become advanced enough to create a substrate-independent consciousness, meaning a mind that can run on a computer. Second, assume that such a civilization would be interested in running detailed simulations of their own past or of other possible realities. Third, assume they could run a vast number of these simulations. If these three things are true, then the sheer number of simulated realities would vastly outnumber the one base reality. Therefore, it is statistically much more likely that we are one of the countless simulated beings than the original organic ones. The laws of physics in our universe, with their finite rules and constants, might just be the programming of the simulation. The Planck length could be the resolution of the cosmic computer. Quantum weirdness, like entanglement, or the fact that a particle's properties are not definite until measured, could be a sign of the simulation optimizing its resources. It does not need to render the particle's properties until a conscious observer looks at it, just like a video game does not render the details of a city on the other side of the map until the player goes there. This is a deeply philosophical idea, but it has a direct connection to the fate of the cosmos. If our universe is a simulation, its ultimate fate is not determined by its own internal laws of physics, but by the simulators. The simulation could be turned off at any moment. The big freeze or big rip might never happen because the plug gets pulled. Our cosmic end could be a simple end program command. Are there any ways to test this? Some physicists have proposed looking for clues. One idea is to look for tiny anomalies in the distribution of high-energy cosmic rays. If space-time is a discrete grid, like a 3D pixel lattice, then particles traveling diagonally across this grid would behave slightly differently than those traveling along its axes. This might create a subtle pattern in the cosmic ray spectrum that would not be there if space-time were perfectly smooth and continuous. So far, no such evidence has been found, but the possibility remains. The fate of our entire cosmos, from the first quantum fluctuation to the last dying star, might be nothing more than a data file on a hard drive in a higher level of reality. Number 10, a quantum leap could create a new universe in a lab. Quantum tunneling is a fundamental aspect of the quantum world. It describes how a particle, like an electron, can pass through a potential energy barrier that it classically should not have enough energy to overcome. It is like a ball rolling up a hill and instead of rolling back down, suddenly appearing on the other side. And this is not just a theoretical curiosity, it is responsible for how the sun generates energy through nuclear fusion and is the principle behind certain types of microscopes. In the 1980s, cosmologists like Alan Guth and Andre Linde applied this quantum idea to the universe itself. In the context of cosmic inflation, they explored the possibility that our universe was created from a quantum tunneling event. Imagine the pre-universe was a state of empty space, a false vacuum with a high energy level. The theory of eternal inflation suggests that this false vacuum state is constantly spawning new universes. A small region can tunnel through the energy barrier to a lower energy state, a true vacuum, like the one we live in. This tunneling event would release a tremendous amount of energy, triggering an exponential expansion.com, a big bang, and creating a new bubble universe. This leads to a mind-boggling and potentially terrifying idea. If our universe was created by such a quantum event, could we create one ourselves? In theory, could a sufficiently advanced civilization concentrate enough energy in a small enough point to trigger a false vacuum tunneling event and create a new baby universe? The numbers involved are immense, far beyond anything we can currently achieve. You would need to create a density of energy equivalent to what existed in the first fractions of a second after the Big Bang. Some calculations suggest this would require creating a tiny artificial black hole that would then evaporate in a specific way. But theoretically, it is not ruled out. If it were possible, what would happen? The new universe would not appear inside our own, and it would likely tunnel out of our space-time, creating its own new bubble of space and time that would rapidly expand, completely disconnected from ours. From our perspective, we might see a small black hole form and then instantly vanish. We would have no way of knowing if we had succeeded, but this brings up a dark side to this cosmic creation. What if the process is unstable? What if instead of creating a separate baby universe, the attempt triggers a vacuum decay event right here in our own universe? As discussed before, this would be a bubble of a new vacuum expanding at the speed of light, destroying everything. An experiment designed to be the ultimate act of creation could become the ultimate act of cosmic suicide, wiping out our entire universe. The fate of our cosmos could, in this scenario, be in our own hands, or the hands of some other hyper-advanced civilization. The end might not come from natural processes like expansion or entropy. It might come from a lab experiment gone wrong. The same quantum principle that may have birthed our cosmos could be the one that is weaponized, intentionally or accidentally, to bring about its end. The universe's fate would no longer be a matter of cosmology, but of engineering and ethics on a scale we can barely comprehend. Number 9, reality only exists because we observe it. The measurement problem is arguably the deepest and most troubling puzzle in quantum mechanics. At its heart is the wave function, a mathematical object that describes all the possibilities for a quantum system. An electron, before it is measured, is not at a single point. It exists as a cloud of probabilities described by its wave function. It is in a superposition of being in many places at once, but the moment we measure it, the moment we look, the wave function collapses and the electron snaps to a single, definite location. The question is why? What is so special about measurement or observation that it forces reality to make a choice? And what constitutes a measurement? Does it require a conscious observer? A physicist named John Archibald Wheeler took this idea to its cosmic conclusion with his concept of the participatory anthropic principle. Wheeler proposed a thought experiment called the delayed choice experiment. In a simplified version, you send a single photon towards a screen with 2 slits. So if you place a detector right behind the slits to see which one the photon goes through, it behaves like a particle and goes through one or the other. If you remove the detectors and instead place a photographic plate far behind the slits, the photon behaves like a wave going through both slits at once and creating an interference pattern. The weird part is this: you can decide whether to put the detectors in place after the photon has already passed the slits. Your choice, made now, seems to retroactively determine the path the photon took in the past. Wheeler scaled this up to the entire cosmos. Imagine a photon emitted from a distant quasar billions of years ago. Its path is bent by the gravity of an intervening galaxy, so it can reach our telescopes on Earth by 2 different paths. This is a cosmic-scale double-slit experiment. We on Earth can choose today how to observe that photon. We can set up our telescope to see which path it took, in which case it behaved like a particle for its entire billion-year journey. Or we can set it up to see if the 2 paths interfere with each other, in which case it must have behaved like a wave and taken both paths simultaneously. Our observation, made in the present, seems to define the reality of what that photon did billions of years ago. Wheeler took this to its ultimate conclusion. He suggested that the universe in its early moments existed as a vast superposition of all possible histories, a quantum fog of potential. It was only when conscious observers like us evolved and began to make measurements by simply looking at the sky that one of those histories collapsed into the concrete classical reality we see. In this view, we are not just passive observers of the universe. We are participants. Our acts of observation reach back in time and give reality to the past. The universe and observers are part of a self-creating loop. The universe creates us, and we, through our observations, create the universe's history. The fate of the cosmos in this picture is deeply strange. What happens when the last conscious observer is gone? Does the universe revert to a state of pure, uncollapsed quantum potential? If reality requires observation to become concrete, then a universe devoid of observers might not have a definite fate at all. It might not end in any meaningful sense. It would simply dissolve back into a superposition of all possible ends, a sea of probabilities waiting for an observer that will never come. The cosmos would end not with a bang or a whimper, but with the closing of the final eye. Number 8. The nothingness of empty space will tear the universe apart. For most of the 20th century, the biggest question in cosmology was whether the universe's expansion would slow down and reverse, leading to a big crunch or continue forever. The answer depended on how much stuff, how much mass and energy was in the universe. In 1998, 2 teams of astronomers made a shocking discovery. They were observing distant supernovae to measure the rate at which the expansion was slowing down. They found it was not slowing down at all, it was speeding up, something was pushing the universe apart. This mysterious something was given a name dark energy. It appears to be a property of space itself. As space expands, more space is created, and so more dark energy appears, pushing everything apart even faster. This is the dominant force in the universe today, making up about 70% of its total energy density. The simplest explanation for dark energy is the cosmological constant, an idea Albert Einstein first proposed and then called his biggest blunder. It is the energy of the vacuum, the baseline energy of empty space predicted by quantum field theory. There is a huge problem, however. When physicists try to calculate how much energy the vacuum should have based on quantum theory, they get a number that is absurdly large. It is 10 raised to the power of 120 times larger than the value we observe. This is the vacuum catastrophe, the worst prediction in the history of physics. Despite this theoretical mess, we can observe what dark energy is doing and project its consequences for the future. If dark energy is a true cosmological constant, a constant energy density for every cubic meter of space, then the fate of the universe is the Big Freeze. The accelerating expansion will carry distant galaxies beyond our horizon, leaving our local group of galaxies isolated in an endless void. The stars will burn out and the universe will become cold, dark, and empty. But what if dark energy is not constant? What if its density increases over time? This hypothetical form of dark energy is called phantom energy. If it exists, it leads to a much more violent and spectacular end, the Big Rip. The scenario, first proposed by Robert Caldwell, Mark Kamienkowski, and Nevin Weinberg in 2003, is a cosmic horror story. As phantom energy's density increases, its repulsive force grows stronger and stronger. At first, it just pushes galaxy clusters apart, but as the end approaches, its power escalates dramatically. About 60 million years before the end, its force will be strong enough to overcome the gravity holding our Milky Way galaxy together. The stars will be flung into the expanding darkness. A few months before the end, it will overcome the gravity holding the solar system together. The Earth will be ripped away from the sun. In the last minutes, the Earth itself will be torn apart. In the final 10, raised to the power of 19 seconds, atoms themselves will be destroyed as the phantom energy overcomes the strong nuclear force. The end is a singularity not of density like the Big Bang, but of infinite expansion rate. The scale factor of the universe becomes infinite. Every single particle in the universe becomes causally disconnected from every other particle. The fabric of space-time itself is torn asunder. The fate of the cosmos is not a slow fade to black, but a sudden, violent annihilation where every structure, from galaxies to atoms, is shredded by the growing energy of nothingness. Number 7, the universe will end in a cascade of evaporating black holes. In 1974, Stephen Hawking made a theoretical discovery that changed our understanding of black holes forever. Until then, black holes were thought to be truly black. Their gravity was so strong that nothing, not even light, could escape. They were cosmic prisms, the ultimate endpoints of matter. Hawking showed that this picture was incomplete. When he combined the laws of general relativity with the principles of quantum mechanics, he found that black holes are not completely black. They glow. This glow is now called Hawking radiation. The process is rooted in the quantum foam of empty space. Pairs of virtual particles and antiparticles are constantly popping into existence and annihilating each other. But if this happens right at the edge of a black hole's event horizon, it is possible for one particle to fall in while the other escapes. The particle that falls in has negative energy, which reduces the mass of the black hole. The particle that escapes becomes a real particle, carrying energy away. To an outside observer, it looks like the black hole is emitting a faint thermal radiation. This process is incredibly slow for large stellar mass black holes. The temperature of a solar mass black hole is only about 60 nanokelvins, far colder than the cosmic microwave background radiation. So, right now, all existing black holes are absorbing more energy from the CMB than they are radiating away. They are still growing, but the fate of the universe is a long game. In the distant future, after all the stars have burned out and the universe has expanded and cooled to near absolute zero, the tables will turn. The universe will become colder than the black holes. Then, and only then, will they begin to lose mass. A stellar mass black hole will take about 10 raised to the power of 67 years to evaporate. The supermassive black holes at the centers of galaxies, with masses millions or billions of times that of the sun, will take far longer. A large one could take up to 10 raised to the power of 100 years to disappear. This is a timescale so vast it is almost meaningless. A Google years. The end of a black hole's life is not a gentle fade. As it loses mass, its temperature increases. The rate of evaporation speeds up. In its final moments, a black hole that started with the mass of a mountain would have shrunk to a microscopic size but would be radiating with incredible energy. In its last second, it would explode with the power of billions of nuclear bombs. This sets the stage for what is called the black hole era of the universe. After the stars are gone, these slowly evaporating black holes will be the only interesting things happening in the cosmos. They will be the last sources of light and energy in an otherwise dark and empty universe. The ultimate fate of the universe is tied to their demise. After the last and largest supermassive black hole finally evaporates in a final flash of high-energy gamma rays, around the year 10 raised to the power of 100, the universe will enter its final stage, the dark era. All that will be left is a diffuse, ever-expanding soup of photons, neutrinos, electrons, and positrons at an incredibly low energy. The last organized structures of matter will have converted their mass back into energy, one final act of quantum fireworks before an eternal silence. The universe's story will end with the quietest, longest, and final fizzle. Number 6, we live in a cyclical universe that bounces back from the brink. The standard Big Bang model has a problem at the very beginning. It predicts a singularity, a point of infinite density and temperature where the laws of physics break down. For many physicists, a singularity is not a description of reality, but a sign that your theory is incomplete. Several theories rooted in quantum gravity have tried to solve this problem by replacing the Big Bang singularity with something else, a big bounce. The idea is that our universe did not begin from nothing, it emerged from the collapse of a previous universe. In this scenario, the universe goes through infinite cycles of expansion and contraction. A previous universe expanded, then its expansion slowed, reversed, and it began to collapse in on itself in a big crunch. But instead of collapsing to an infinitely dense singularity, quantum gravity effects take over at extreme densities. These quantum forces would create a powerful repulsive pressure, halting the collapse and causing the universe to bounce back outwards, beginning a new cycle of expansion, our Big Bang. One of the leading theories that incorporates this idea is loop quantum gravity LQG. LQG proposes that spacetime is not continuous, it is made of discrete, indivisible quantum loops or atoms of spacetime. There is a minimum possible size. You cannot squeeze space down to a volume smaller than this quantum limit. In the context of the Big Crunch, as the universe contracts, it eventually reaches this minimum size, the point of maximum density. It cannot get any smaller. The quantum nature of spacetime itself provides the repulsive force that triggers the bounce. The singularity is avoided. Another model that leads to a cyclical universe comes from string theory and M theory, specifically the ekpyrotic or cyclic model developed by Paul Steinhardt and Neil Turok. In this model, our universe is a three-dimensional brane, like a membrane existing in a higher dimensional space. There is another parallel brane nearby. The Big Bang is caused by the two branes slowly moving together and colliding. The collision releases a massive amount of energy, heating our brane and triggering the expansion we observe. The branes then move apart, cool down, and eventually the cycle repeats as they are drawn together again for another collision billions or trillions of years later. In both the LQG and Brane World versions, the fate of our cosmos is tied to the beginning of the next one. Our current expansion, driven by dark energy, presents a problem for these models. If the universe expands forever, it will never collapse for a crunch and a bounce. However, some versions of the theory propose that dark energy might not be constant. It could be a form of quintessence that will eventually decay, allowing gravity to take over again and begin the collapse. If these models are correct, the ultimate fate of our universe is not an end, but a transition. The Big Freeze would just be a temporary phase before the eventual collapse. All the structures we see, galaxies, stars, planets, would be destroyed in the Big Crunch, their matter and energy recycled to fuel the next Big Bang. The universe would be eternal, not through infinite expansion, but through infinite cycles of death and rebirth. The quantum nature of spacetime itself ensures that there is no final end, only another beginning. Number 5, all matter will eventually disintegrate into nothing. We are made of atoms. Atoms are made of electrons, protons, and neutrons. We take it for granted that these particles are stable. And an electron seems to be truly fundamental and stable. But what about protons and neutrons? For a long time, the proton was also thought to be eternal. The conservation of baryon number, a law in the standard model of particle physics, seemed to guarantee its stability. A baryon is a type of composite particle made of 3 quarks, like protons and neutrons. The law states that the total number of baryons in any interaction must remain the same. Since the proton is the lightest baryon, it has nothing to decay into without violating this law. However, in the 1970s, new theories emerged that tried to unify the fundamental forces of nature. These grand unified theories, GUTs, proposed that at very high energies, like those in the early universe, the strong, weak, and electromagnetic forces were all just different aspects of a single, unified force. A key prediction of most GUTs is that the sacred law of baryon number conservation is not absolute. It can be violated. This means that protons are not, in fact, stable. They can decay. The predicted process is incredibly rare. A proton would decay into lighter particles, like a positron and a pion, which itself would then decay into photons. The predicted lifetime of a proton is enormous, at least 10, raised to the power of 34 years. This is many, many orders of magnitude longer than the current age of the universe, which is about 1.4 x 10 raised to the power of 10 years. So we do not see protons decaying around us. Physicists have built massive experiments to try and catch a single proton in the act of decaying. The Super Kamiokande detector in Japan, for instance, is a gigantic tank holding 50,000 tons of ultra-pure water surrounded by thousands of light detectors. The idea is to watch a huge number of protons, the ones in the water molecules, for a long time, and hope to see the telltale flash of light from one of them decaying. So far, after decades of searching, not a single proton decay has been definitively observed. This has ruled out the simplest guts, but more complex theories predict even longer lifetimes, pushing them beyond our current ability to detect. But if protons do decay, even on these immense timescales, it has a profound consequence for the fate of the universe. It means that all matter as we know it is fundamentally unstable. In the far, far future, long after the stars have died and the galaxies have dispersed, the universe will enter the degenerate era. It will be populated by the cold, dead remnants of stars, white dwarfs, neutron stars, and brown dwarfs. Over trillions upon trillions of years, these objects will slowly, atom by atom, dissolve into radiation. The protons and neutrons that make them up will decay. Eventually, all the baryonic matter in the universe, every disk, every planet, every dead star, will evaporate into a bath of photons and leptons. This is a more complete and fundamental heat death than just the stars burning out. It is the death of matter itself. The ultimate fate, in this scenario, is a universe devoid of any structure. Not even atoms, just a thin, cold, ever-expanding soup of photons, neutrinos, electrons, and positrons. The quantum process of proton decay ensures that, in the end, there is literally nothing left. The grand cosmic story, which began with the creation of matter from energy, will end with the slow, patient conversion of all matter back into energy. Number 4, our universe is just one page in an infinite book. The many worlds interpretation MWI of quantum mechanics is one of the most bizarre and yet beautifully simple ways to solve the measurement problem. It was first proposed by Hugh Everett III in his 1957 doctoral thesis. Everett's radical idea was this: the wave function never collapses. All the possibilities described by the wave function are real. Every time a quantum measurement is made, the universe splits. Take the example of an electron spin, which can be up or down. Before measurement, it is in a superposition of both. When you measure it, the MWI says that the universe splits into two branches. In one branch, you measure the spin as up. In the other branch, a copy of you measures the spin as down. Both outcomes happen. Both universes are equally real. You, the observer, are also split, with each version of you experiencing one of the outcomes and being completely unaware of the other. This process of splitting happens constantly with every quantum event. An uncountable number of parallel universes are created every moment, branching off from each other to form a vast, ever-growing multiverse. There is a universe where you chose a different breakfast this morning. There is a universe where the dinosaurs were not wiped out by an asteroid. There is a universe where every conceivable outcome of every quantum event has been realized. This has a profound implication for our place in the cosmos. Our entire observable universe, from the Big Bang to its ultimate fate, is just one world or branch among an infinite number. It is one page in an infinite book of cosmic histories. The fate of our specific universe might be a big freeze, but that is just the story of our branch. In other branches, the story could be different. Perhaps in some branches, a random quantum fluctuation could reverse the expansion or create a new Big Bang. Perhaps in others, the laws of physics themselves branch into different possibilities. The MWI, when combined with cosmology, suggests that all possible cosmic fates are realized somewhere in the multiverse. This also provides a different perspective on probability. Why does a radioactive atom have a 50% chance of decaying in a certain time? In the MWI, it is not a matter of chance. In 100% of cases, the atom both decays and does not decay in separate branches. The 50% probability we perceive is just a reflection of our position as an observer who can only experience one of those branches. The ultimate fate of the multiverse itself is simply to keep branching. It does not have an end in the same way a single universe does. It is an infinitely complex, ever-growing structure of all possible realities. Our universe's heat death is just the end of one chapter. The book itself goes on forever. There is no final state for the whole system, only an endless proliferation of possibilities. It is the ultimate expression of the quantum nature of reality, where anything that can happen does happen somewhere. Number 3, dark matter is a signal from a parallel universe. About 85% of the matter in the universe is not the normal atomic matter we are familiar with. It is something else, something invisible. We call it dark matter. We know it exists because we can see its gravitational effects. It is the extra gravity that holds galaxies together and keeps galaxy clusters from flying apart. Without it, the structures we see in the cosmos would not exist. We just do not know what it is. The leading candidates are new types of subatomic particles, like WIMPs, weakly interacting massive particles, or axions, which are predicted by theories that go beyond the standard model of particle physics. Despite decades of searching in deep underground labs and with powerful colliders, we have found no direct evidence for these particles. This has led some physicists to consider more exotic possibilities. One of the most intriguing comes from string theory and the idea of extra dimensions. The theory that gave us the cyclic universe model, the brain world scenario, offers a novel explanation for dark matter. In this model, our three-dimensional universe is a brain floating in a higher dimensional space called the bulk. The theory proposes that the particles and forces of the standard model, photons, electrons, quarks, and the forces that govern them are confined to our brain. They cannot leave it. They are stuck like water droplets on a sheet of glass. But gravity is different. In some of these models, gravity is not confined to our brain. It can leak out into the bulk, and gravity from the bulk can leak into our brain. This opens up a fascinating possibility. What if there is another brain, another universe, parallel to our own, just a short distance away in the extra dimension? We would never be able to see it or interact with it directly, because the light and matter of that universe would be stuck on its own brain. But we could feel its gravity. In this scenario, dark matter is not a new type of particle. It is just the gravitational influence of ordinary matter stars, galaxies, and gas in that parallel universe leaking across the small dimensional gap and affecting our own. The dark matter halo we detect around our galaxy could be the gravitational shadow of a parallel galaxy existing just millimeters away in a direction we can never point to. This idea is testable. In principle, if gravity can leak between dimensions, it might behave in slightly different ways at very small scales than predicted by Newton's law of gravity. Experiments are being conducted to look for these tiny deviations at sub-millimeter distances. So far, none have been found, which constrains these models but does not rule them out entirely. The fate of the cosmos is interwoven with this idea. If dark matter is the gravitational echo of a parallel world, then the evolution and ultimate fate of our universe are not independent. The cosmic web of dark matter that dictates the large-scale structure of our universe would be a reflection of the structure in another. The fate of that other universe could influence our own. Would the two brains ever collide again? Would they drift apart? The destiny of our cosmos might be gravitationally tethered to the destiny of an invisible parallel reality. Number 2, our universe was born from a quantum burp. The universe seems to be incredibly flat. In cosmological terms, flat means that on the largest scales, Euclidean geometry works. Parallel lines stay parallel. The angles of a triangle add up to 180 degrees. This is a very specific condition. If the total density of matter and energy in the universe were even slightly higher than a certain critical density, the universe would be positively curved, like the surface of a sphere, and would have eventually collapsed. If it were slightly lower, the universe would be negatively curved, like a saddle, and would have flown apart too quickly for structures to form. The fact that our universe is so close to perfectly flat is a puzzle called the flatness problem. Another puzzle is the horizon problem. When we look at the cosmic microwave background CMB radiation, the afterglow of the Big Bang, we see that it has an almost perfectly uniform temperature in all directions, about 2.725 Kelvin. This means that regions of the universe that are now on opposite sides of the sky, billions of light years apart, must have been in thermal contact with each other in the early universe. But according to the standard Big Bang model, these regions were never close enough for light or any other influence to have traveled between them. They were outside each other's causal horizons, so how did they come to be the same temperature? In 1980, a physicist named Alan Guth proposed a solution to both problems with a single, powerful idea, cosmic inflation. He proposed that in the first tiny fraction of a second after the Big Bang, from about 10 raised to the power of 36 to 10 raised to the power of 32 seconds, the universe underwent a period of hyper-accelerated exponential expansion. During this brief instant, the universe expanded by a factor of at least 10 raised to the power of 26, going from a size smaller than a proton to the size of a grapefruit. This incredible stretching of space solves the flatness and horizon problems. Any initial curvature the universe had would be stretched out to flatness, just as the curvature of a small balloon becomes flatter as you blow it up to a huge size. And the entire observable universe we see today originated from a tiny causally connected patch before inflation began. Everything was in thermal contact, which explains the uniform temperature of the CMB. What drove this inflation? The theory posits a quantum field called the inflaton field that filled all of space. This field was in a high-energy, false vacuum state. The energy of this field acted like a powerful temporary form of dark energy, providing the repulsive force that drove the exponential expansion. Inflation ended when the inflaton field decayed to its low-energy, true vacuum state, dumping its energy into the universe and creating the hot soup of particles that we associate with the Big Bang. In this sense, the Big Bang was not the beginning, but the end of inflation. Here is the deepest connection to the cosmos. Inflation took microscopic quantum fluctuations, the same virtual particles of the quantum foam, and stretched them to astronomical scales. Tiny, subatomic ripples in the inflaton field were blown up to become the seeds of all cosmic structure. The slightly denser regions became the spots where galaxies and galaxy clusters would later form. The slightly less dense regions became the great cosmic voids. The pattern of these fluctuations is imprinted on the cosmic microwave background. When our satellites like MAP and Planck measured the tiny temperature variations in the CMB, they found a pattern that perfectly matched the predictions of inflation. We are, in a very real sense, seeing the fossilized evidence of quantum fluctuations from the first moment of time. This leads to the idea of eternal inflation. In many models, once inflation starts, it never completely stops. While our region of space, our bubble universe, stopped inflating, other regions of the inflaton field are still expanding exponentially. These regions are constantly spawning new bubble universes, each with its own Big Bang. Our universe is just one burst, one quantum burp, in an eternally inflating fractal-like multiverse. The ultimate beginning of our cosmos was a quantum event, and its ultimate context is an endless sea of other quantum beginnings. Number 1, the fate of the universe is written in the energy of nothing. The most profound and puzzling connection between the quantum world and the fate of the cosmos is also the most direct. It is the energy of empty space itself. We have a name for it in cosmology, dark energy. We have a name for it in quantum physics, vacuum energy. They should be the same thing. And their story is one of complete catastrophic disagreement. According to quantum field theory, the vacuum is not empty. It is filled with a sea of virtual particles constantly fluctuating in and out of existence. Each of these fluctuations has a certain amount of energy. To find the total energy of the vacuum, you are supposed to add up the energy of all the possible fluctuations. When physicists do this calculation, they run into a disaster. The math says the sum is infinite. To get a sensible answer, they have to assume that the calculation does not work all the way down to infinitely small scales. They cut it off at the Planck length, the smallest meaningful size in physics. Even with this cutoff, the predicted value for the vacuum energy is enormous. It is about 10 raised to the power of 121 times larger than the energy density of normal matter in the universe. If the vacuum energy were this large, its gravitational effect would be overwhelming. It would be a repulsive force so powerful that it would have ripped the universe apart in the first fractions of a second. Atoms would never have formed, galaxies would be impossible, the universe as we know it could not exist. But we know we exist, and in 1998 we discovered that the universe's expansion is accelerating. There is a dark energy, a form of vacuum energy, but its value is tiny. It is cosmologically significant now, but it is incredibly weak. The observed value of dark energy is about 120 orders of magnitude smaller than the value predicted by our best quantum theories. This is the cosmological constant problem, or the vacuum catastrophe. It is the single greatest discrepancy between theory and observation in all of science. Something is wrong. Either our understanding of quantum vacuum energy is profoundly mistaken, or there is some unknown physical principle that cancels out almost all of this energy, leaving just a tiny residual amount. And physicists have proposed many ideas. Perhaps there is a symmetry, like supersymmetry, that causes the energy contributions from different types of particles to cancel each other out almost perfectly. Perhaps the value is set by anthropic selection in a multiverse-only universes with a tiny value survive long enough to produce observers. Perhaps our theories of gravity need to be modified. No solution is currently accepted. But this tiny leftover dreg of quantum energy is the most important factor in the long-term fate of the entire cosmos. It is this minuscule energy of nothingness that is pushing everything apart. It dictates that our universe is heading for a big freeze. It is responsible for the cosmic event horizon that will eventually hide all other galaxies from our view. It is the architect of our future isolation and the eventual heat death of the universe. The ultimate destiny of everything, the final chapter of the cosmic story, is being written by the most poorly understood and badly predicted number in all of physics. The greatest mystery of the quantum world is the very same force that is sealing the fate of the cosmos. The beginning, the end, and everything in between is tied to the strange, paradoxical, and powerful nature of empty space.